Hi, my name is Lucas Weintraub, and today we're going to look at logarithmic expressions. Alright, so what are logarithmic expressions? Logarithmic expressions are kind of like the inverse of exponential expressions. So if you were to write something in exponential form, you can undo it with a logarithm. And so the need for logarithms comes up whenever we have equations that use exponentials. For example, when we have addition, like x plus 2 is equal to 7, we need subtraction to solve this. So on the right side here, you would have x minus 2 on both sides, and then that is equal to x is equal to 5, which is equal to x. And then multiplication, you need division to solve this. So this would be 2x over 2, which is equal to 7 over 2, which is equal to x. For x squared is equal to 7. To solve that, we need to be able to square root. So square root of x squared is equal to plus or minus the square root of 7. And that is equal to x. So this has two solutions. And then 2 to the x is equal to 7. How do we do that? We can't use subtraction, division, or taking the root to solve this. So now we need a new function, a new operation, and it's a logarithm. So in this case, it would be log base 2, which is equal to log base 2 of 7, which is the same as x. And we're going to go more into that over here. So logarithmic form, how do we do it? It's another way to write something in exponential form. So if you have a to the b power is equal to c, we can rewrite this as the logarithm base a of c is equal to b. So basically, if you have two numbers, a and c, the logarithm is kind of like the power. So when you have a logarithm, you want to ask the question, a to what power b is equal to c. So a to what power b is equal to c. So let's do some examples. Let's say we have 2 to the power of x is equal to 4. To solve for x, we can put this in logarithmic form, and that would be log base 2 of 4 is equal to x, because 2 to what power is equal to 4? 2 to what power is equal to 4? This says the same thing. 2 to power of x, or some unknown power, is equal to 4. And it just so happens that 2 to some power that equals 4 is going to be 2, because 2 squared is 4. 2 times 2 is 4. Let's see if we have 3 to the x is equal to 1/3. We can represent that in logarithmic form as log base 3 of 1/3 is equal to x. So we're asking 3 to what power is equal to 1/3? 3 to what power is equal to 1/3? And that would happen to be -1, because 3 to the -1 power is equal to 1/3, because anything to a negative power is a reciprocal. So hopefully that gives you a better understanding of logarithmic form. So now we're going to move on to graphs. that use these logarithms. And I want to introduce it with the pH scale. So let's say that you have some water and it has a pH level of 7. And then you have some acid that has a pH of 3. The first idea is that maybe the water is just 4 more acidic than the acid with a pH of 3. But that's not the case. And it's not 4 times more either. In fact, the water is 10 to the 4th times larger. So each time that you get 1 pH higher, it's 10 times more basic, or 10 times more alkaline. And if you were to get 1 more less in the other direction, it's 10 times more acidic. So something with a pH of 0 is going to be 3 times more acidic with something that has a pH of 3. And it's going to be, did I say 3? Sorry, I meant to say 10 to the 3rd power times more acidic, aka 1,000. So this is 1,000 times more acidic. And this is going to be 1, 2, 3, 4, 5, 6, 7, 10 to the 7th power times more acidic than the water with a pH of 7. So instead, logarithmically scaled graphs don't measure the acidity, or the actual amount of acidity in it. It measures the magnitude of acidity. So kind of like the power or the exponent. What these actually represent is 10 to the 9th, 10 to the 10th, 11, or 10 to the 11th, 10 to the 12th, and so on. And so really what you're plotting is the power of that in base 10. So now we're going to explore this a little more. Let's say you have a function like 2 to the x. Here's what it looks like on a regular graph. So it increases really fast, and it's kind of hard to fit it all on one page. And if you were to shrink it down, then all the numbers right here would be just so close together, just all be almost like a flat line, because if you wanted to make everything fit, you had to squash everything. So the solution is a logarithmically scaled graph. We saw earlier that everything increased by powers of 10. So kind of like increasing exponentially. So if the y-axis increases exponentially with our exponential graph, then we should have something that's probably like a straight line. And so we can see that right here. So before exploring that, some points on the regular graph are 1, 2, 2, 4, 3, 8, because 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, 2 to the fourth power is 16, 2 to the fifth power is 32, which is way up here, and that's why we don't want to use a normal graph. We want to use a logarithmic graph. And so here, each equally spaced interval is logarithmically scaled. So instead, this is not going up by 4s like it was over here. This is times 2. This is also times 2 times 2. So it's going up by powers of 2, not by intervals of constant length. So now we have a really nice straight line because all the points are plotted to just their power. So 2 to the first power is 1. And so that is at a height of 1 length because it's the first power. And this goes up by powers. And so if we're plotting 2 to the third, we're just going to go up 1, 2, 3 because this is 2 to the third. Same thing for 4. 2 to the fourth is 16, or just 4 because it's the fourth power. And the same goes for all the other points on here. 2 to the 0 is 1. And so we're just going to go to 0, the 0th power. And that's interesting to note because the bottom of this scale is just going to be 1 instead of being 0. So the origin of this graph is 0, 1, not 0, 0. So that's one difference between the logarithmically scaled graph and the normal graph. Now, I want you to try to plot these points on a graph of base 10. And pause this for a second to see if you can try it out. Maybe get a piece of paper or just guess where it's going to be. But I'm going to work it out right now. So here, 1, 100 is going to go right here. Because the input of x is 1. This is x and this is y. The input is 1 and the output is 100, which is right there. This next one, 5.5 and 10 to the 5th. We're going to go to 5.5, which is right there, and 10 to the 5th, which is right here. Because 10 to the 5th is 100,000, or it's just the 5th one up. 1, 2, 3, 4, 5. That's 5. 1, 2, 3, 4, 5. And the reason why we can do that is because this is logarithmically scaled. These go up by powers of 10. And so if it's the 5th power, we just go up 5 times. Now, this one is a little tricky. So we know that the x is somewhere here because it says 9. And so it's going to be at 9. But where do we plot 50? So 50, a good guess would be right in the middle. So in between 100 and 10, because it's kind of like, it sounds like the midpoint between them. But that's not the case on a logarithmically scaled graph. What we're plotting is the power. So what we want to find out is log base 10 of 50 is equal to x. In other words, 50 is equal to 10 to what power? And so you can take a calculator out and try this for yourself. And what you would do is press the log button on it. This is a TI-84 calculator, by the way. So you would do log, and the log, just log, is another way to show log base 10. If you want to do log of other bases, you would need other buttons. But here there's a nice shortcut. So log base 10 of 50. And that is 1.6989 and so on, which is approximately 1.7. So instead of putting 50 in between here, which is like 1.5, because this is kind of like a height of 1, this is a height of 2, and this is where we guessed 50 would be, in between those. It's actually a little bit above that, because log base 10 of 50 is approximately 1.7, and that is a kind of 1.7 up from the bottom. So it's kind of, if you're going to go up 1.7 amount. if I were to tell you to plot maybe 9 and then 10 to the 1.7, it'd be much easier to do that because all you'd have to do is just go up 1 and then a little bit 0.7. But if it's not in the base of the scale, because this is base 10 and this is base 10, but if it's not in base 10, you would have to convert it to base 10 or whatever base the scale is. All right, so hopefully you got those right when you tried those out, and if not, hopefully you can watch this video again or other videos online to explain it. So now I want to get into an application of logarithms and logarithmic scales and functions and whatnot. So there's something called the Richter scale, which is a scale that describes the magnitude of mountains and their earthquakes. And the formula from some website is the energy in joules of an earthquake is given by log base 10 of the energy is equal to 4.4 plus 1.5 times the magnitude of that earthquake. So that's a lot of fancy words. If you didn't know before, joules is a unit of energy, and the magnitude represents how strong the earthquake was. And let's say you were given the magnitude and you wanted to find the energy. Well, you can start off by, actually give it a go yourself and then pause this video and then I'm going to do it right now. So what is the energy of an earthquake with a magnitude of 7? That's a really strong earthquake, and let's see how much energy that is. So first we're gonna plug in what we know. I'm gonna replace energy with E, because that's shorter. I'm gonna put 4.4 plus 1.5 times 7. If you were to put that in your calculator, that is roughly equal to 14.9. Well, not roughly, it's exactly that. And now, since earlier we learned that exponentials and logarithms are inverses, we can undo this logarithm of base 10 by putting this in the exponent of 10. So it kind of looks like this. So 10 to the power of log base 10 of E is the same as 10 to the 14.9th power. And we can do that because if we were to do 10 to this power, it's the same as 10 to this power because we already saw here that these are equal. But now here's the good part. 10 to the power of log base 10 cancels because those are inverses, or the inverse functions. So what you're left with is E, or the energy in joules, is equal to 10 to the 14.9th power, which is approximately 7.94 times 10 to the 14th, or 7.94, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 joules. So that's a lot of energy, and something of magnitude 6 would be a lot less energy than that, and 5 would be a lot less than that, and it would go exponentially down. And so just to summarize what we learned today. So for logarithms, we learned that logarithms and exponentials are inverses. Why would this work? There we go. Inverses. So if you do one, and then you do the other, then you get back what you started with. We also learned how to write logarithms. And so we did some examples of converting some things to exponential or logarithm and vice versa. We also looked at the pH scale, an example of how logarithms are used to measure the acidity of water. And we also looked at the Richter scale to measure the magnitude of earthquakes. And so both of these are science applications. The pH is an example of chemistry, also used in biology, and the Richter scale is an example of physics and probably geology and all more earth sciences. And then we also looked at some graphs of functions that increase exponentially and how that can be represented with logarithmic scales to make them much easier to read, because now it all fits. So hopefully now you can walk away with a better understanding of how logarithms work and how they're used in real life.